In this lesson, we're going to learn about the longest word that I know. It's called differentiability. You can double check me, but I think it's 17 letters long, and I challenge you to think of a word that you know that's much longer than that. So we'll define it, and we will also define the relationship between continuity and differentiability. A function f of x is differentiable at x equals c if the derivative f prime of c exists. You'll notice that I underline differentiable and derivative. So although differentiable is a kind of a formal word and it's a little intimidating, all it really means is that the function has a derivative. And luckily for us, both the words start with a D, so that helps me remember that when I hear differentiable, they're really just talking about a derivative. There are two requirements for a function to be differentiable. First and foremost, the function must be continuous at x equals c. If the function is not continuous, we don't even look to see what the derivative is doing around that value x equals c. We stop there. If the function is continuous, we then must look at the left derivative and the right derivative and ensure that they are equal. This might remind you of a process that we used for limits in looking for where the limit exists, or if the limit exists, that the left limit and the right limit must be equal. This is similar, but we'll be looking specifically at the derivative from the left and the right. Let's talk about what makes a function not differentiable at any x value c. And the first is basically a contradiction of the first requirement of differentiability, in that if the function has any type of discontinuity, a point, a jump, an infinite asymptote, or an oscillating trig function, then it automatically disqualifies the function from being differentiable. If the graph is continuous, there still might be a couple things that disqualify it from being differentiable, the first of which is a vertical tangent. Vertical tangent means that the graph goes vertical or has vertical slope at some value c, and that slope we call undefined, or the slope doesn't exist. And we know derivative means slope, so if there's no slope or undefined slope, we do not have a derivative there as well. So here's just two really simple sketches of right in the middle of these two curves. I hope you would agree that the slope goes perfectly vertical for just that one x value. And so that graph would not be differentiable at those vertical tangents. The other thing we need to look out for is when the left and right hand derivative are not equal. This creates what we call a corner or a cusp. A corner is most famously recognized in the absolute value graph, and a cusp is a lot like a corner, but it's a little more rounded. It reminds me of the birds that we used to draw in our elementary school paintings. But the corner and cusp both have very abrupt changes in slope, so that when you look at the left-hand slope and the right-hand slope, they are very different at that corner or cusp. And so they would not be equal, and that disqualifies the function from being differentiable at those vertices. Our learning target said that we're going to define the relationship between continuity and differentiability. So continuity is what we talked about in Unit 1 with the left and right limits being equal, and the point meeting up at those left and right limits is the same y value. If a function is differentiable, then it is automatically continuous. And I hope this makes common sense because continuity is a requirement for differentiability. It's the first and most important requirement. So if we know for a fact that a function is differentiable, we can correctly assume by its requirement that the function must be continuous. So I have this D implies C. My arrow is a little exaggerated, but I was trying to reach between those two statements. It's really important to recognize or to realize that that relationship does not work in the other way or in the other direction. So if a function is continuous, it may not be differentiable, and we saw 4 perfectly good examples up here. Vertical tangents, corners, cusps, those are all continuous, but they are not differentiable. So that is a one-way relationship. One more way to put that relationship in context, if you're a more visual person, you might remember from geometry learning about Venn diagrams. And so this outer circle or bigger circle contains all functions that are continuous, but only a portion of those continuous functions meet the requirements for differentiability. So that differentiability lives inside continuity and not the other way around. So I hope those two explanations help you understand the relationship between those important concepts. Let's take a look at our first graphical example. We're going to analyze at all 5 function values, or x values I should say, if the graph is either continuous, differentiable, both, or neither, and just further examine that relationship between the two concepts. I myself find it easier to look at continuity first, so I'll do this first row, and then I'll start thinking about differentiability to all those x values as well. So remember, the easiest way to think about continuity is, can I trace this graph without lifting my pen or pencil? And I do a pretty good job through 0, 1, 2, 3. I can trace it without lifting my pen. I guess I could actually do that as I say I'm doing it. And the only time I have a problem here is when I get to x equals 4. So I'm going to go ahead and say yes for 0 through 3 and no for 4. So I've got my continuous graph from x equals 0 through x equals 3, and when I reached x equals 4, I found that there was a jump discontinuity in the graph. So I said no, and I specified the reason why not. When I go to my row on differentiability, that x equals 4 is actually the easiest place to start, because I know automatically when I get a no for continuous, I don't even have to think that hard. It is not going to be differentiable no matter what the graph looks like there. So that discontinuity disqualifies it from being differentiability. Lots of long words in the video today. So I have to look a little more carefully at all these x values to make sure it's differentiable. I already know it's continuous, but I'm looking for those kind of odd things, vertical tangents, any corners or cusps that I can find. I hope you don't mind me jumping around at the values, but when I look at 1, x equals 1, and I can trace it without any corners or cusps. Same with 3. Those are both nice smooth curves without any sharp abrupt changes in slope. I feel confident in saying that yes, both of those x values are differentiable. The other two, I hope you can also see that there's some funny business going on there. The 2 is the most obvious of those values. At 2, we have a sharp corner, or you can call it a cusp. Those two words are really used interchangeably, but it's anytime you see that abrupt change in slope. At x equals 0, this one's a little bit hard to spot. We can overlook it pretty easily, but I hope that when we're talking about it, you can see that the graph actually goes vertical right at x equals 0. So we're going to say no for differentiability because we have a VT, or a vertical tangent. I'd like you to try the next example, the same examination. Go ahead and determine at the x values if the graph is continuous, and then look at the differentiability. And when we get together in class, I'll have you discuss in your pods what your answers are and if you have any discrepancies to work out. Then I'd like to look at this piecewise function as a class and look at to see if the limit exists, to see if it's continuous, and to see if the function's differentiable. All 3 of these procedures are pretty similar, so it's nice to see them side by side to see how they are different. So I'll see you in class.